The theory of continental drift was proposed by Alfred Wegener in 1915, stating that all the continents in the Earth were once joined together around 200 million years ago in what he called a supercontinent known as Pangaea. So, due to forces arising from the rotation of the Earth, Pangaea split and drifted away and formed what we know today as continents. The first evidence to support this theory is known as continental repeats. As early as the 17th century, Francis Bacon speculated that opposing shorelines of various continents fit together, kind of like pieces of a jigsaw puzzle. Sir Edward Bullard, with the aid of a computer, actually produced a more accurate repeat according to the continental shelves of each continent, which are actually found 2,000 meters below sea level. These evidences suggest that continents may actually have been together at one point of time and have drifted apart over the years. The second evidence to support this theory comes from structural as well as lithological evidence. Continents are made out of long chains of fold mountains known as shields. These are long, narrow, and fairly differentiated. They are made up of the roots of ancient mountains and can be traced from one pond end in one continent to another. Examples of these include the chain of mountains running down through Scotland, which can be geologically linked to the chain running down from Newfoundland to the Appalachians in the United States. Lithological evidence, which refers to evidence found from rock types in a continent, includes link-up of various rocks in one continent to another. One example is the link-up of the distinct bands of Permian rocks deposited in India and Australia around 230 to 270 million years ago. The sequence of rock types as well as thickness in each band of rocks corresponds across two countries, which suggests that during the time of deposition of these rocks, the two countries were actually joined together and drifted apart to form India and Australia as we know today. Rocks containing iron-rich minerals are formed, they cool from their molten state, and when they cool from beyond their Curie temperature, they become magnetized in accordance with the prevailing magnetic field, which is the Earth. As long as the rock is not heated again near its Curie point, permanent record is frozen into the rock and can be kept for millions of years. Similarly, when magnetic particles are deposited into the Earth, they are aligned parallel to the lines of the Earth's magnetic field. As long as the age of the rock is known or determined, this can be used to find the position of Earth's North Pole during the time when these rocks are formed. The polar wandering curve of a continent is the track plotted by following the movement of the North Pole relative from the continent over a period of time. That the poles of the Earth is known to move, but it is found that the polar wandering curve differs from continent to continent. This suggested that there is relative movement between the continents, which causes the change in orientation of the polar wandering curve. Paleoclimatic evidence. About 300 million years ago, glaciation occurs exclusively in the southern hemisphere. When glaciers move, they actually deposit rocks on the oceanic crust as they scrape past the surface. However, these rocks have been found now at zones near the equator, which suggests that the land with which the rocks have been deposited on have actually shifted from the southern hemisphere up to the equator. Similarly, corals have only been known to form in warm waters within 30 degrees of the equator. However, coralline rocks have been found in the Arctic Circle, which is way up, in the northern hemisphere. So this suggests that the corals have actually formed in the tropics, then shifted upwards on drifting continents. Paleontological evidence. Species of animals are seen to develop independently in Africa, Australia, and South America, suggesting that their ancestors once lived on the same land, and they split into different groups and developed differently after Pangaea split. By studying fossil population and evolutionary trends, the land movement through geological time of these continents can actually be established. However, there are many weaknesses in this theory. Although there are many scientific observations to support Wegener's theory that the continents drifted apart from each other, most geologists and geophysicists rejected his theory because, firstly, no one could explain the force behind the movement of the continents, and also another issue is that Wegener was not an expert in this field. The theory of plate tectonics. Plate tectonics can be explained by mantle convection currents as well as seafloor spreading. In 1929, Arthur Holmes proposed that the internal heat from Earth's core causes convection currents to be formed in the liquid asthenosphere, which is found in the Earth's mantle. Basically, heat from the Earth causes the hot material in the asthenosphere to rise to the base of the lithosphere, where it moves laterally, it cools and becomes denser, and descends to be reheated again. So this process is repeated over and over again, causing convection currents to be formed in the mantle. These convection currents pull the lithosphere plates on top of it along the mantle, and this phenomenon can actually be used to explain earthquakes, volcanoes, fault mountains, as well as the drift of the continents. Theory of seafloor spreading. In 1960, a geologist from Princeton University, Hess, proposed that the ocean floors are spreading apart due to the convection currents in the mantle. Basically, these convection currents causes the ejection of lava, which is where an oceanic ridge occurs. The convection currents in the mantle pulls the two sections of lithosphere away from the ridge towards the deep sea trenches. There, the descending convection current causes the crust to descend into the mantle to be reabsorbed. This way, the entire ocean floor can be completely regenerated in 200 to 300 million years. The areas where the crust descends into the mantle are known as deep sea trenches or Benioff zones. This process is known as subduction. These theories covers the key idea of plate tectonics. There are just supporting evidence to justify the general theory, which are: first, thermistor probe readings have shown that the temperature over mid-oceanic regions have been higher than surrounding areas, testifying the claim that lava is being ejected at these areas. Similarly, temperature readings have been shown to be lower at subduction zones, which can be explained by the fact that the mantle is cooled as the cold crust descends and is reabsorbed. Second, the level of seismic activity over mid-oceanic regions have been higher, showing that there's actually crustal movements within these areas. Third, the Earth's gravitational field has been found to be slightly higher at subduction zones, indicating that the material below the surface is less dense than the surrounding. This supports the theory that the less dense ocean crust descends into the mantle. As sediments are deposited away from the ridge as seafloor spreading takes place, one should find younger sediments on areas that are nearer to the ridge, and older as well as thicker sedimentation which occurs at areas further from the ridge. In 1968, a venture was started that proved this hypothesis to be true. And lastly, the Vine-Matthews hypothesis, which goes as such: as rocks cool from the lava ejected over the mid-oceanic regions, they become magnetized in accordance with Earth's magnetic field at the point of time where they solidify. It has been shown that Earth's magnetic field reversed itself numerous times over its history. If that was the case, the magnetism in the rocks should record this phenomenon. For example, rocks which are formed further away from the mid-oceanic ridge should reflect the same direction in Earth's magnetic field during the time that they solidify. However, when the reversal of Earth's magnetic pole takes place, newer rocks which are formed will reflect an opposite direction. This pattern of alternating directions of Earth's magnetic field should carry on as rock samples are analyzed further and further away from the ridge. The Vine-Matthews hypothesis was proven in 1966.